Good afternoon, all the students present here. Today, we'll be continuing our unit number 4 on nozzles and their applications. Okay. The contents of the topic called nozzles is isentropic flows through nozzles, types of nozzles, ejectors, variables, interactions, thrust reversal, and some of the numerical problems. Basically, what is a nozzle? So nozzle is defined as a place where you try to accelerate the velocity which is coming outside from your, either if you are talking about the gas turbine engines, you are talking about the jet engines or the rocket engines. So you are trying to eject the exhaust velocity which is coming outside your engine. Okay. So generally it is a duct which having a cross sectional and converts pressure energy into kinetic energy and accelerating the fluid into high velocity. So basically when you talk about the jet velocities, it is considered to be VE, whereas in your terms of jet engines, it is considered to be thrust of that engine. Okay. So typically the nozzle plays a vital role in the engineering domain, where it is been used for the power generation, industrial process, and for the propulsion devices it is simply used for jet engines and rocket engines. So nozzle design directly governs the thrust, specific impulse, and performance. These are the performance parameters of your jet engines, where you will be dealing with different kinds of performance parameters which include your thrust, specific impulse, and the efficiency of the performance parameters in terms of the nozzle. Clear? So when we move ahead, so the governing equations of the isentropic flow, already you know what are these isentropic flows in detail, where you have been covered these all isentropic flows in the thermodynamics and basics of your air breathing propulsion, where you know the continuity equation rho a v is equals to constant, or rho 1 v1 a1 is equals to rho 2 a2 v2, basic fundamental continuity equation, where you have already covered it in your fluid mechanics. And the energy equation, when we are considering the energy equation, we are considering it as steady and the adiabatic flow, where the h, what is the h, is called as the metacentric height in the fluid flow, plus half mv square, where we consider the mass as the unit, so it is considered to be v square is equals to h naught stagnation enthalpy. Okay. Isentropic flows or the isentropic relations, where you will be talking about the different types of temperature ratios, pressure ratios, and the density ratios. The first equation talks about the temperature ratio at the inlet and the exit, pressure ratio at the both the cases, and the density ratio, where m indicates your Mach number, gamma which is your Cp by Cv, the value which is 1.4, generally we consider it as T0 and P0 are your stagnation oblique total conditions for your temperature and pressure. Together these relations, when we try to design any kind of a nozzle, these considerations or the relations should be taken into consideration, and then we should go for the design. So if you observe the image on the right side of the slide, where you have a inlet, where you have a throat, and you have a flow at the exit. Okay. So when you talk about the inlet, it is a converging duct till the throat, and after the throat it is a diverging duct. Okay. So the converging duct is itself indicating the area is getting reduced at the throat, the minimum area throughout the nozzle, and after that it is an expansion one. Okay. So when you talk about the inlet, the flow here, we are talking about the flow of the, either it is a exhaust gas or else the flow through a pipe, flow through any kind of a jet. Okay. When we move forward, so generally you all know what is a Mach number, and now in the nozzles we are talking about the Mach number versus area velocity relationship. So precisely when we talk about this area velocity relationship, there is a flow physics which is involved into it. So initially I am considering a small elemental area which is represented by dA divided by the total area, which is A, which I am writing in terms of Mach number and in terms of velocity. So the relation which is written here is dA by A is equals to m square minus 1 multiplied by dV by V, where dV, dA are small elemental area and small elemental velocity. A and V are your cross sectional area, and the total velocity or the exit velocity. Okay. So before proceeding to these cases, when we are talking about the right side wala image, you just see the right side case, where m square minus 1, this is the condition for your Mach number. When it is negative, then the dA and dV are the opposite signs, where the flow is in the convergence section, where it is accelerates the flow towards the sonic condition. When is equals to 1, generally Mach number is equals to 1, or that condition is equals to 1 or equal to 0, is implicating at the throat, where your Mach number will become 1. So at that throat, the minimum area, as I already told, the throat is a condition where the minimum area of your nozzle, where the Mach number is coming to be 1. So that condition is called as a choke nozzle, that I will be explaining you in the next slide. it is when it is more than 1 or greater than 1, which is generally we call it as a positive. That if it is positive, the same sign convention is there, and it is now moving, the flow is moving towards the diverging section, and now it is continuing to be accelerated value. So this part, after the divergent section, this part will be considered to be your exit part of your velocity. Okay, so once that exit part of the velocity is reached, then you have the value called a by a star. Generally it is called as a by at or ae by at, so which is your exit area divided by throat area. Okay, that exit area divided by throat area, why we are taking it into consideration, whether when we are trying to design any kind of a nozzle, we are supposed to take these design consideration into consideration, and considering all these parameters, we will be designing our nozzle. Okay, where ae by at, here I wrote it as a by a star. So generally in the numericals, it will be asked regarding ae by at, which is area at the exit divided by area at the throat. Okay, if you observe the image, the conditions of the image are the pattern of the flow which we are talking about. The flow, whether it is subsonic, whether it is supersonic, or whether it is hypersonic, or at the throat, whether it is a choked condition. Okay, so as already mentioned, a star is the area at the throat. The sonic conditions, generally that sonic condition is required to either, if the flow is very fast, we are trying to decelerate it. If it is very low, we are trying to accelerate it. So that cases can be achieved. So when we are moving ahead, so basically we have some different types of nozzles as already discussed in the earlier classes. So these are some of the different types of nozzles and their specifications in terms of Mach number and their diverging sections. Okay, first when we see the convergent type of section, already in the previous image I have shown you the flow through your convergent divergent section along with the throat. So if I consider only the first part, that is called as the convergent section. Second one is your convergent divergent nozzle. Next one is your bell or contoured nozzle. Next one is your conical, annular, and the selection of the nozzle is based on your pressure ratio, speed, weight, and other parameters which are involved when you are considering for the performance of that nozzle. Okay, so when you see about the convergent nozzle, convergent type of nozzle, the accelerations of the flow where the Mach number is equals to 1 at the exit, and it is very basic kind of a design which can be used in your turbojet engines, turbofan engines, or the industrial jets. Okay, when we are talking about the convergent divergent nozzle, so this convergent divergent nozzle is designed in such a way where at the throat compulsory the Mach should be reaching to 1. Okay, so that condition itself implies where you are trying to use a convergent divergent nozzle where the flow should be decelerated at the initial case in the convergent section, and later on it starts acceleration, or the acceleration of that flow will be increased to the supersonic or the more higher speeds. Okay, coming to your bell or the contoured nozzle, so it is a curved wall aligned flow axially, eliminating divergence losses, where due to this divergence there is a huge reduction in the area. That reduction in the area to be overcome, so that we are trying to do this. This is a standard kind of a type of a nozzle which is used in high performance rockets where you require very high amount of specific impulse and the thrust that can be measured. The conical one is the straight cone. So you can you are already familiar with the type of called the cone. So it is a similar type of a cone where you try to cut it from such section across the cross area, and next the divergence section is implied there. So simple and made, but loss of thrust due to flow divergence angles, which is we call it as an alpha. So due to which the losses are more. So this is the one of the disadvantage of this nozzle. Next one is your annular type. In the next image I will show you the next slide, I will show you the image of the nozzles and what are the losses had been there. Next one is the annular flow, where the spike generally we use it for the cases called to create the ramps and all. So these kind of nozzles are the huge research is going on the aerospike nozzles and all. So as already told, the choked flow, when Mach number is brought to 1, already you have know the shock interactions in your inlets. So where the shock swallowing has been done at the forward case, second at the lip, at the inlet cases. So doing that operations, the Mach should be brought to 1 at the throat. Okay, so moving further, the types of nozzles, I will be showing it to you an image. So observe the image in this way. First observe the left side image, left side top image, the types of nozzles. Next we will go with the thrust repulsor and the choked condition. Okay, first observe the left side top image where we already discussed about the types of nozzles. Already I have listed out here convergent, convergent divergent, and the plug nozzle. Okay, so first one, if you see the first image where we have V0 and P0 are the inlet pressure and inlet velocity before entering the nozzle. Okay, at the end we have PE and VE. The condition would be high pressure, low velocity. Next one would be low pressure, high velocity. Okay, based on your Bernoulli's equation, you know the conditions where the pressure is increasing, the velocity is getting reduced, and the other case the velocity is increasing, the pressure is getting reduced. Now here what we are trying to do, based on the geometry of the nozzle, we are achieving these two conditions. One, the pressure is low, and another one, the velocity is more at the exit of the nozzle, and vice versa at the inlet of the nozzle. Same goes with the convergent divergent nozzle. Again, this convergent divergent nozzle can also be called as D-level nozzle. Okay, the convergent divergent nozzle can be called as CD nozzle, D-level nozzle, and the convergent divergent nozzle. Here what happens, the pressure which is at the initial case, the conditions will remain the same. Pressure will be more, velocity will be less. Okay, at the throat there would be small change in those parameters. The pressure will be getting more, velocity will be getting less. After that again the pressure gets down and the velocity gets increased using the geometry of this nozzle. Okay, coming to the plug nozzle, as high central body is a plug, reduces heat transfer to the nozzle walls used in the rocket engines precisely. Okay, the above ones or the above two can be used both for the jet and the rocket engine, where precisely the plug nozzles can be used for the rocket engines. Okay, so where again the parameters will be same at the initial cases, and at the end the velocity should be more, where we are expecting VE as the more value, which is your thrust. Okay, now coming to the below image, we talked about the choked condition of the nozzle, where I am trying to get the Mach number at the throat, which is supposed to be equal to 1. If you observe the image which is below, the stagnation temperature, stagnation pressure are indicated as P0 and T0. We are considering, for our case, it is as a subsonic flow, where I am considering Mach number is less than 1. So at the throat, I am trying to increase that subsonic flow till the Mach number is equals to 1. Generally, you call it as the transonic or the transflow, where this from the transition from subsonic to supersonic is happening. Later on, the Mach number is increased from is equals to 1 to greater than 1 based on the geometry. Okay, so at the end we will be receiving the velocity which is VE and the pressure which is VE. Due to the vortices or the cases where the exhaust is being trying to go, we will be generating a term called back pressure, which is giving the, which is already we have shown at the end of the nozzle. Okay, so here when you talk about the conditions of your throat or the choked condition nozzle, the Mach number already we discussed. At the throat it should be is equals to 1. Upstream of the throat the Mach number which will be less than 1, and at the downstream of the throat it should be supersonic, where the Mach number should be more than 1. The mass flow rate should be maximum and constant to give upstream conditions. Okay, where you already know, due to the continuous inlet from the components of the inlet and the compressor, we get the continuous combustion. To get the continuous combustion, we require the flow should be continuous. So we are keeping the uniformity in the mass flow rate, and then if we write the relation between area Mach number relation, the AE by AT or the A by A star can be written as 1 by m square bracket 2 by gamma plus 1 into gamma minus 1 by whole relation can be written here, where the Mach number we are considering it to be 1. So how did we get this relation? From the isentropic flows, and from that isentropic flows, when we try to derive those equations, we will be trying to get this. So when we go for the last case of this image, where we are talking about the thrust reversal in the jet engine. So basically thrust reversal can be considered is, you know, you are required to produce the thrust to drive your propulsive device or any kind of a jet engine. Okay, so but if I try to generate the thrust in the reverse direction, that concept is called as a thrust reversal. I'll come a bit late to this point or the concept called thrust reversal. So before proceeding for the thrust reversal, there are some points to be covered in the nozzles, then we will come with the thrust reversal. Okay, so what would be the performance parameters? As already every component has some such of the performance parameters. In such cases, we also have the nozzle performance parameters, which include the coefficient of velocity, thrust coefficient, discharge coefficient, and the nozzle efficiency. Okay, so we will be trying to derive this efficiency of the nozzle in a short while, where the velocity coefficient is the ratio of ideal isentropic exit velocity to the actual. In short, we are talking about VE divided by V actual. Agreed? Yes, no, maybe. So it would be the actual divided by the ideal case. So that we will be representing it as C suffix V, and typically this value would be around 0.95 to 0.99. And coming to your discharge coefficient, it would be the ratio of masses now. So the coefficient of velocity would be the ratio of velocities, ideal divided by the actual. Coming to the discharge coefficient, it would be the ratio of the masses. It is considered to be the actual mass divided by the ideal mass, and it is in the range of 0.96 to the 0.99, and it is denoted by C suffix D. And the most important parameter in the performance of the nozzle is your thrust coefficient, which is denoted as CF. It is the ratio of, now as the name itself, it is indicating it is a thrust coefficient, where it is talking about the ratios of the thrust, actual thrust divided by the ideal thrust. Okay, it is denoted as CF. Coming to the efficiency of the nozzle, again this efficiency of the nozzle we have the derivation, but for the case of the consideration we will be looking at the efficiency as a one of the performance parameter, which is your ideal enthalpy drop to the actual enthalpy drop. Okay, so this efficiency is theoretically noted as 0.92 to 0.98, but actual engines may not be operating at these conditions. They will be a bit low to this efficiencies based on the design consideration, back pressure, losses, considering the frictional losses, heat losses, all those things. So this would be operating not exactly in this condition, but approximately similar to those cases. Okay, so moving further, so these are some of the operating conditions. So these are some of the operating conditions of the nozzle. So now when you talk about the nozzle, we have only seen the nozzles in terms of convergent, divergent type of nozzle. There are some of the nozzles which are also considered to be expanded, over expanded and under expanded nozzles. I will be showing it to you how these expanded nozzles will be there. So if I consider perfectly under expanded nozzle, then the relations for the pressure, flow and the thrust are noted down here. So first one, PE is equals to PA, where PE is your exit pressure, PA is your, what would be your PA? PA would be your either the atmospheric pressure, or if I am considering the pressure inside the propulsive device, that can be written as PS. Okay, so why we are writing it as PE is equals to PA? To satisfy the continuity equation. Okay, so that if I achieve that PE is equals to PA, then the flow, when we call it as the supersonic flow in the thrust equation also, where you will be neglecting the term called PE minus PA into V infinity. So that term will be neglected for the supersonic flow. Coming to the second case where PE is more than PA. Now when we consider the PE is more than PA, that is considered to be under expanded nozzle. Okay, so that under expanded nozzle, how it would be, I will show it to in the next one. So the flow behavior would be ideal, no external waves, which are your shock waves, expansion fan at the exit. Now when we talk about these plumes already I told the exhaust gases, once the exhaust is coming, so those smoke or the gases which are included, those are called as plumes. Okay, so thrust, we get the optimal thrust at the design altitude. So again we have design altitude, all those altitudes which would be covered in your aircraft performance and stability, where there are different types of altitude, design altitude, pressure altitude, temperature altitude and so on. Okay, there are some thrust losses and which can be recoverable in the plumes. Okay, coming to the second type of nozzle, which is over and severely or over expanded nozzle. So one is the under expanded nozzle, another one is the over expanded nozzle, where P is less than PA, which we consider that case as the under expanded or over expanded nozzle, where P is far less than PA, which we call it as severely over expanded nozzle, which we can also be considered as the variable area or variable geometry nozzle. I will be showing it to you. So now here in this case, the flow is undergoing the interaction of the shocks. So precisely in this case, we will be getting the oblique shocks at different locations. Okay, so oblique shocks at different locations can be considered here. Next, the normal shocks inside the divergent section. Already you know this shock interactions and all. So these shock interactions will be happening at different locations, and this shock interactions will also try to get into the divergent section. Coming to the concept called thrust, flow separation accepts, symmetry in the side loadings on the nozzle walls, significant thrust loss, critical risk in the rocket design. So one should be able to attain the minimum amount of thrust losses, where this try to create differences or the losses due to the shock waves which are generated. Okay, so moving further, so some of can be used as the ejector nozzles, where This ejector nozzles are high velocity at the primary jet when we try to go. In the short span of time, if we want the more amount of jet or high jet at the time of short period of time, we go with these cases, and we will be mixing both of them at the case. So if you see the right side image, this is the image for the mixing. So these kind of images you will be seeing in the more related to your rocket propulsion subject, where the ducted rocket engines, these kind of images can be called as your ducted rocket engines, okay, where additional combustion chamber will be given after your nozzle to burn the extra amount of fuel to get the more thrust. Okay, so that would be your primary jets exit at the high velocity, creating low pressure zone. Secondary fuel is drawn and mixed with the primary steam. As in our case, we call it as, for the air breathing propulsion, we call it as the afterburner methodology. So whereas in your rockets, it is called as ducted rocket engines. Okay, so it is the combined flow. There is a mixing chamber, diffuser. Diffuser is again placed based on the requirement. If suppose I want to decelerate the flow, I will be using the diffuser. If not, we will be not be using the diffuser. Okay, area ratio mixing, all those things can be done. So as I mentioned, afterburner nozzles in the military jets, where in the jet engines you will be using the afterburner. Jet pumps, ejector refrigeration, altitude simulation, test facility. Augmentation, already you know methods of thrust augmentation, where we talked about the different kinds of thrust augmentation methods. One is the afterburner, another one is the water injection, next one is the fuel injection cases. So those cases can be achieved with the secondary fuel injection system or the additional combustion chamber, which we call it as the ducted engine in the rocket cases. Okay, moving further. So as we were talking about the nozzle, which is overly expanded. Okay, so if you observe the image, we have the nozzle which is drastically expanded. Okay, so these kind of nozzles are called as your variable area nozzles. Okay, when you talk about this variable area, the area can be varied based on the operation. Generally, these are observed many types. You will be observed these kind of nozzles in your jet engines, where the opening and closings of the nozzles will be happening. So generally, that is also called as your flex nozzle, another type of the nozzle. So that another type of the nozzle is your flex nozzle, and that comes under this VAN, which is your variable area nozzle. Okay, so flex nozzles are optimally single point design or the single design point. At they can be operated at thrust level. As the thrust level, altitude, speed changes, the fixed nozzle becomes an over and under expanded, cutting its efficiency. To overcome that, if I required a more thrust, I will be opening the mouth of the nozzle where I required the more thrust. If I required a less amount of thrust, I will be trying to close that. This can be achieved only based on the variable area nozzle. So other name can be called as the flex nozzles. Okay, this flex nozzle generally you will be observing in the fighter jets and all. Okay, so here it can be used with different kinds. So the some of the examples are your F-16 and F-22, where you have used this variable area nozzles or the flex nozzles. Also, you can be using these kind of nozzles in your ramjets and the scramjet engines, where the velocity which has to be attained will be very more, as the vehicles will be moving with supersonic and hypersonic speeds. Okay, when we move further, so this is your nozzle flow interactions with the adjacent surfaces. Okay, so if you observe the image, you came with some concept which is called Coanda effect. Okay, in the earlier cases of your fluid mechanics, when we were discussing about the topic called continuity equation, Bernoulli's equation, there is something which is called as a Coanda effect. Okay, I hope I am not supposed to repeat this Coanda effect in this class. So that Coanda effect can be used for the plumes which are coming outside. So that plumes will be considered to be a vortices or the circulation zones, where the exit jet can be disturbed using these Coanda effects. Okay, so these are considered to be your flow interactions with the adjacent surfaces. Okay, when we talk about these adjacent surfaces, we have cross flows, blockages, impingement, and these can be overcome based on the different methodologies. Okay, so these methodologies can be attained based on the designs of your nozzles. So once these designs of the nozzles are done, so these blockages can be reduced, effective nozzle area, and upstreaming the bow shocks. Already you know what is a normal shock, what is an oblique shock, what is a bow shock. Generally it is formed in terms of a bow or else a triangle which can be formed at the sharp conical edges. Okay, so these can be attained using these things. And impinging on your wings, fuselage, and the ground or the thermal loadings can be causing your induced lift or the downward wash, which results in your drag generation. Okay, moving further, so we were talking about this shock waves. Okay, observe the left side, right side, top and bottom images, where the first one is showing you the over expanded, and next one is showing the under expanded. Okay, so if suppose there is a jet which is coming out of your nozzle, so these are called as your shock diamonds. Okay, the small diamond cases where you will be talking, so these are your shock diamonds which are formed in the exhaust of your rockets or the jet which is coming out of your nozzle. So this can be clearly seen when they are been performed on the static tests of your rockets. Okay, these shock diamonds will be attained in such a way where the length of the shock diamonds will be implementing the flame length, all those things. Okay, so if we see the over expanded case, the oblique shock at the lip angle inward, which is angled inward towards your nozzle type, waves get reflected as a expansion waves. Periodic Mach diamonds, generally these are called as your Mach diamond, shock diamond, which can be clearly seen in the blue colors when it is been done on the static firing. Okay, for the under expanded cases, expansion fans outward the lip, plumes, which is considered to be a huge plume which is coming out of your nozzle, where that plume will be controlled on the firings when they've been done using different methodologies. Okay, so barrel shocks at the plume boundaries all then be considered. Moving further, so as we were supposed to discuss on the topic called thrust reversal. Okay, generally what is a thrust reversal and why do you need this kind of a thrust reversal? Okay, in the IAE also we came across the concept called air brakes. Okay, where we have used the spoilers, air brakes in such a way. Here also the engine can be utilized not only to develop the positive thrust, but also it can be utilized in generation of the negative thrust, which is we here call it as the thrust reversal. Okay, so thrust reversal can be considered generally why it is needed. It is needed when the wheel brakes alone fail on the wet, icy or the short runways, reduce brakes wear and tear or the landing distance by 35 to 40 percentage. So how it can be done, I'll be just letting you to provides backup decelerations in the brake failures scenarios. Okay, so generally to visualize this case, when the jet aircraft lands, there is a parachute which is coming outside your nozzle is considered to be your thrust reversal case, one of the thrust reversal case, where it creates more drag into it. Again, it is something which is called as a governing principle when we talk about the retarding force or the reversed thrust components plus drag. Okay, so it is the bonus for the drag. Generally, we are not expecting any kind of a drag, but at the time of high speeds should be decelerated very fast. Along with the drag, we require the thrust reversal. Okay, generally this is called as your thrust vectoring control as well. So which is another terminology which is your TVC, generally we call it as. So where you try to vector the thrust in the different directions. So here it is the thrust reversal where you try to exactly opposite of the flow and it gets started there. Moving further, so these are some of the types of your thrust reversal. Okay, bucket, cascade, targeted, cold stream. Okay, so two doors block the nozzle exit. So there is something which is called as a nozzle opening and closing. So the opening or closing of the nozzles will be closed with the two sides of a doors. So that can be considered where you don't require to generate the thrust, but you are trying to cut short the thrust. Okay, next blocker or the reverse cascade where the cascade vanes or the angling exhaust at the different angles can be done. Precisely, this can be used for your smaller aircraft. Next one is your rotating petals reflex exhaust at the 45 degrees angles, which try to used for your layer jet, or simply you can call it as the business class aircraft, which is your 6-seater, 10-seater aircraft or the smaller aircraft. There you can be used. Next one is your cold stream, which is precisely used in your high bypass engines, which is in our case it is your turbofan engine, where the cold stream will be passed over a high exhaust stream where the cold stream is trying to reduce the temperature where the exhaust is getting out from the nozzle. These are some of the different types of thrust reversals. There are some performance limits and moving with the numericals. Okay, so before proceeding with the numericals, we'll stop the lecture here, and if you have any doubts, we'll be discussing those at the earliest. Thank you.